In this video, we're going to go over the gas laws. We're going to start off by going over Charles' law. So gas laws will work for the ideal gases that we discussed earlier. And there's several gas laws that we're going to focus on. And the idea is that each gas law relates a variable to another. So for example, you have Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, combined gas law, and the ideal gas law. And there's also Dalton's partial pressures law as well. So for example, you can see here Boyle's law tries to relate pressure and volume. Charles' law tries to relate volume and temperature. Gay-Lussac's law relates pressure and temperature, so on and so forth. In this video, we're going to focus on Boyle's, Charles, Gay-Lussac's, and the combined gas law. And in the next lessons, we're going to take a look at the remaining gas laws. As usual, it's a good idea to always watch the preview video, the preview materials, so you can take a look at the gas laws and overview over here, and a quick little demonstration over here as well. So let's go ahead to our handout and fill it out together. We're going to go over each gas law. First, we'll start off with Boyle's law or Charles' law, and then we'll go on to the other laws. So we'll go over what the law means, and then afterwards we'll do some practice problems relating to that law on a mathematical level. So our first relationship is going to be Charles' law. And that states that at constant pressure, so pressure needs to be the same, temperature and volume are directly proportional to each other. So that means basically that if one goes up, the other goes up as well. So as temperature of a gas increases, so does its volume, and the other way around. So that will work as long as the amount of gas in your sample and the pressure are constant. Basically, you only want to change one thing at a time when it comes to this law here for Charles's law. So pressure is going to be the same. Temperature and volume are directly proportional to each other. How would we write that relationship out in a simpler way? We could say that volume is proportional to, this means proportional to, temperature. Essentially, if one goes up, the other goes up. If one goes down, the other goes down. For example, if temperature doubles, then volume will also double. So how can we express Charles's law mathematically? Well, we simply put V1 over T1 is equal to V2 over T2. The V1 is the initial volume. The T2 is the final volume. And the T1 is the initial temperature. And the T2 is your final temperature. When you're using this Charles' law formula, you want to make sure, and all the formulas in this unit, you want to make sure your temperature is in Kelvin. So your temperature needs to be in Kelvin. So if temperature is given to you in degrees Celsius, make sure you convert to Kelvin. Here you can see a graphical representation of Charles's law. So you can see that temperature is on the x-axis, and then volume is on the y-axis. And as temperature goes up, as long as pressure is constant, you can see that the volume increases as well. So essentially, if we have a temperature over here, and we double that temperature over here, you can see that the volume doubles. So if this was 5, this would be 10, for example. Okay, and that's Charles's law. Now we're going to take a look at how we can explain Charles's law with the kinetic molecular theory. So let's say, for example, you were to increase temperature. What that would do is it would cause your volume to increase as well, because they are proportional to each other. So if temperature goes up, then volume goes up. And why is that? Well, as you increase temperature, the particles are going to have more kinetic energy, and therefore they're moving faster. And because they're moving faster, they're going to have more collisions with the walls of the container, and the container is just going to expand as a result of that. So the particles are basically getting more energy, moving faster, they're moving away from each other, they're taking up more space, which is why their volume has increased if you provide them with more energy. So you can see this over here in this picture. We heated up the sample. So for example, this is our initial temperature over here, T1, and the particles are not taking up too much space. They're only taking up this much space over here. But now if we go to T2 where we increase the temperature, you'll notice the particles start moving faster and push this piston up, and they take up a lot more space here. So now they've taken up a lot more space. Our V2 is higher than our V1 because we've increased the temperature from T1 to T2. So if we were to decrease temperature, then our volume would decrease. When you decrease the temperature, you've reduced the kinetic energy, so there's less kinetic energy. And so the particles move more slowly and they come closer together. There's also fewer collisions, and so the container is going to decrease in size. So if we went from this temperature here, the higher temperature, to the lower one over here, well then the piston would come back down. This over here is the piston, and the particles occupy less space when you have a lower temperature. If you were to take a balloon that's inflated and you were to put it in your fridge, you would notice that over time it would look smaller. And then if you were to take it out of your fridge, you notice over time that it would look larger. You didn't change the number of particles in there. What you did is you just increased or decreased the temperature, and it caused the particles to either move out, space out more, and take up more volume, or move in and take up less volume. So again, it's important to understand that the pressure is constant when we're doing these experiments, and you didn't change the amount of gas in there. So the gas is taking up more space, not because there's more gas particles, but because you gave more energy to move around and to push against the containers of the wall. So let's take a look at a sample problem. We have a balloon. It's inflated with air in a room in which the temperature of the air is 295 Kelvin. And it has a volume of 650 milliliters. The balloon is put into a refrigerator at 277 Kelvin and left long enough for the air in the balloon to reach the same temperature as the air in the refrigerator. Predict the volume of the balloon, assuming that the amount of air has not changed and the air pressure in the room and then the refrigerator are the same. So there's a lot to unpack here, and we're going to take a look at exactly how we can go ahead and do that. So in a question like this, we need to take a look at what's changing and what's not changing. So let's go take a look at our given data here. We have our initial conditions. So we have a T1 initially that's 295 Kelvin. Okay, that's our initial temperature. I'm going to put this in my given information. And we also have our initial volume. So V1 is 650 mils. Now, this can stay as milliliters. You can convert it to liters as well. But what's important is that you're consistent with your volumes. As long as they're both milliliters is fine, or they're both liters is fine. You just have to be consistent. And for our final conditions, we said that the balloon went into a refrigerator where the temperature actually went down, 277 Kelvin. And we want to know what the new volume of the balloon is going to be. And we told you that the pressure and the amount of air in the balloon did not change. You didn't lose air, and you didn't add air in, and the pressure in the environment is the same. So pressure is not changing. So pressure is constant. So really the only thing that's changing here is the volume. And so this is a relationship between temperature and volume and temperature, I should say. So this is a relationship between temperature and volume. And so if it's a relationship between temperature and volume, we know we're going to be using Charles's law, which is V1 over T1 is equal to V2 over T2. So we know that this is one of those volume is proportional to temperature types of questions. If you increase the temperature, you increase the volume. If you decrease the volume, or if you decrease the temperature, you decrease the volume. So let's go ahead and write out our equation. So this is our given information here. And now I'm going to go ahead and write out an equation. Actually, first I'll write out my unknown, just to write out what I'm looking for. So my unknown is V2. And I'm using the guess method here. If you have other methods you're comfortable with, you can do that or follow whatever your teacher tells you to use. My equation is going to be that V1 over T1 is equal to V2 over T2. And now I'm going to solve over here. So I'm going to substitute and solve, I should say. So I'm going to substitute all my information in. So my V1 is 650 mils over my T1, which is 295 Kelvin, is equal to my V2 over 277 Kelvin. And now I'm just going to solve by cross multiplying or by sending my 277 over here to the other side because I want to get V2 alone. And so that'll be that the V2 is equal to 650 milliliters times 277 Kelvin. And the reason it's multiplied is because it was divided on this side, and now we send it to the other side, it becomes a multiplication, over 295 Kelvin. And so our units will cancel out, Kelvin and Kelvin cancel out, and we're left with milliliters. So let's try that out in our calculators. 650 times 277 divided by 295, and we get that it's approximately 610.3389831 milliliters or V2. So we're going to do our therefore statement. So GUESS and an S are statement here. Therefore, the V2 is approximately, and we're going to make sure it has a proper number of sig figs. So it looks like 2 sig figs is my smallest number of sig figs. So it's approximately, I can round down to 610 milliliters. And that makes sense. We went from a higher temperature to a lower temperature, right? So we decreased the temperature, which means that our volume should decrease. And so the particles come closer together, they have less kinetic energy, and so they would take up less space, 610 milliliters, as opposed to 650 when it was out of the refrigerator. So always check to see that your answer makes sense. Let's go ahead and try the next question, where we have a birthday balloon that's filled with helium to a volume of 1.50 liters in an air-conditioned room of 294 Kelvin. The balloon is taken outdoors on a warm, sunny day and left out as a decoration. The volume of the balloon expands, and that makes sense. You take it to a warmer area, so the particles have more kinetic energy, they space out more and just expand. Assuming that the pressure and the amount of gas remain constant, so pressure and amount of gas are constant, what is the air temperature outdoors in Kelvin? So we're looking for the unit in kelvins. So let's write out our given information again. So we have our initial volume of our balloon was 1.50 liters. We have our initial temperature was 294 Kelvin. And we have our final volume is 1.55 liters. And we want to find our T2. We're asking what is our final temperature outside. So that's what we're looking for. That's our unknown, T2. And we can write out an equation. We know this is a volume is proportional to temperature problem. So we know that's Charles's law. So it's going to be V1 over T1 is equal to V2 over T2. And so we're going to go ahead and substitute and solve. So our V1 was 1.50 liters over our T1, which was 294 Kelvin, is equal to our our V2 1.55 liters over our T2. And so we just need to rearrange this to find our T2. So basically I'm going to send T2 to the other side and then send all these to the other side, and they become the opposite of whatever they're doing. Because whatever's a division becomes a multiplication, whatever's a multiplication are on top of the numerator there becomes a division. So we're going to get T2 is equal to 1.55 liters multiplied by 294 Kelvin over 1.50 liters. And so we're going to cancel out our units there, liters and liters, and we're left with Kelvin. So we'll get 1.55 times 294 divided by 1.50, and I get 303.8 Kelvin. And then I'm going to put a therefore statement. So therefore, the temperature outside, the T2, is approximately, we need to make sure we have the proper number of sig figs. It looks like I have 3 sig figs as my smallest amount, so we can round up to about 304 Kelvin. And this makes sense. At the lower temperature, we had a volume of 1.50 liters. When we put it outside, the temperature, the volume went up. So the gas particles took up more space. And if volume went up, that's because temperature went up, right? So remember that they're proportional to each other. So our volume went up, which means that was because our temperature outside was higher than the temperature inside. And so this here is our temperature, or the air temperature outside, which led to that increase in volume. We'll do one more example together to see if this is Charles's law over here. So we have a certain amount of gas occupies a volume of 60 liters at 300 Kelvin. Find the temperature of the gas which has a volume of 100 liters. So we're going to be assuming here that the amount of gas is not changing. We're going to be assuming that the pressure is also constant in this case as well. And we want to find the temperature, of the gas at which has a volume of 100 liters. So we're assuming that basically what we're trying to tell you here is, here's our given information. We have our volume 1 is equal to 60 liters. We have our T1 is equal to 300 Kelvin. And what we're telling you is, well, now the gas has a volume of 100 liters. So what was the temperature of that environment to lead to that? That's what we're trying to get at here. So this is another temperature and volume situation where we have our volume is proportional to the temperature. And so the volume increased here. So for the volume to increase, what must have happened to the temperature? Well, if the volume increased, that's because the particles moved farther away from each other, which means that we probably have a higher temperature. So I'm just thinking about that before I even solve the problem. And so since this is a volume and temperature situation, we're going to have our V1, Charles' law here, over T1 is equal to V2 over T2. And so what will that give us? Well, let's go ahead and plug in our information and solve. So we're going to have our 60 liters over our 300 Kelvin is equal to 100 liters over our T2. And then we're just going to rearrange. So our T2 is going to be equal to our 100 liters times 300 Kelvin over 60 liters. We can cross out liters and we're left with Kelvin. So we have 100 times 300 divided by 60. And let me just make sure I got that right. So we have our, oh yes, that's right. So that's 500 Kelvin. I think I put the wrong answer in the handout. It should be 500, so I made an error there. So 500 Kelvin is correct. Then we can put our therefore statement. So therefore, the final temperature is approximately 500 Kelvin, and 1 sig fig is the smallest amount of sig figs that we have. So 1 sig fig is correct there. And so that would be our final temperature, and it makes sense that temperature would have increased to lead to the higher volume overall. So remember that in these questions here so far, the temperature was always given to us in Kelvin, but if the temperature was not given to you in Kelvin, you'd have to convert it to Kelvin from degrees Celsius. And remember also, for the volume, you can use milliliters as long as you understand that if you're using milliliters, your final volume answer is going to be in milliliters as well. And you could have used liters, as long as you understand that if you use liters, your final volume answer would be in liters as well. So just be consistent with what you're using there. You have a choice when it comes to that. Um, so one really neat application of Charles's law is a hot air balloon. So basically, what we do is we heat up the air with a flame over here, and it causes the particles to spread out throughout the balloon and expand the volume there. So, and that allows the hot air balloon to fly up in the air. And so we're not necessarily adding more particles there. What we're doing is we're causing the particles that are there to space out more and increase their volume. So that's one important application of hot air balloons, and you should be able to explain that using Charles' law. And I'd like you to also watch this quick demonstration of Charles's law and just briefly describe it in the space over here. So maybe make a little label diagram to explain what's going on with some particles and try to use the kinetic molecular theory and Charles's law in order to explain that demonstration.